A real wormhole, the wave that arrived wrong. On the 21st of May 2019, something passed straight through the Earth that was smaller than the width of a proton, and I mean that literally. A ripple in space-time, stretching and squeezing every atom of this planet by a fraction of a single proton's width, at the end of a journey of more than 17 billion light-years. We know how to read ripples like that now. Nearly always they're the dying cry of two black holes falling into one another, and after a decade of listening we have a good ear for how that cry ought to sound. This one didn't sound like it. It was far too short, and the first half of it simply wasn't there. For 6 years nobody could get that signal to behave. Then, in 2025, a group of physicists put forward an explanation so strange that I still catch myself going back to check whether I've read it properly. What if this wave was never made in our universe at all? What if it came to us through a wormhole from a universe on the other side? I'd like to take that idea seriously enough to actually test it, which means working out what a wormhole would have to be, why entanglement and the shape of space-time may turn out to be one and the same thing wearing two different hats, and whether we can honestly say we've overheard a neighbouring cosmos. Begin with the detection itself. When LIGO recorded the wave, now catalogued as GW190521, the first thrill had nothing whatever to do with other universes. If the masses had been read correctly, this was the first intermediate mass black hole ever caught in the act of being born. Everything we'd seen up to that point fell into two camps with an awkward gap sitting between them. Stellar mass black holes, below roughly 65 solar masses, are the corpses of individual stars. The supermassive ones, from hundreds of thousands up to billions of solar masses, sit in the hearts of galaxies. Theory insists there ought to be something in the middle, 100 to 100,000 suns, and every simulation nods along in agreement. We had simply never watched one turn up. This wave said that at last we had. 85 solar masses on one side, 66 on the other, merging into a single object of 142. Do the subtraction and you land on the part I have never quite got used to. 9 suns worth of matter stopped being matter and left as pure gravitational energy in under a second. 6 years on, a team led by Chi Lai at the Hangzhou Institute for Advanced Study went back through that signal and could not make it fit. Whatever they tried, GW190521 refused to look like an ordinary merger. And that is the point at which a very odd idea starts to look worth entertaining. What a merger is supposed to sound like. To see why this signal is strange, you first have to know what a normal one looks like. When two heavy objects spiral together, neutron stars, black holes, the collision shakes space-time itself, and the shaking spreads outward in every direction. Some of it eventually washes over the Earth, where laser interferometers pick it up. LIGO at 2 sites in America, and Virgo just outside Pisa. From the shape alone we can say what collided, how heavy it was, and roughly how far away it all happened. A black hole merger arrives in 3 movements, and each one leaves its own fingerprint. The first movement is the in-spiral. 2 black holes circling each other are quietly bleeding energy away as gravitational waves. Lose energy and the orbit tightens. A tighter orbit means faster motion. Faster motion means stronger gravity between them, which bleeds the energy away faster still. The process feeds on itself. So they wind inward, quicker and quicker, and the signal climbs steadily in both pitch and volume. Push it through a speaker and you hear a rising whoop, which is exactly why everyone calls this sound a chirp. The second movement is the collision itself, and it's finished almost before it begins. One single instant where the wave reaches its greatest height and its most violent squeeze. The third is the ring down. A newborn black hole doesn't show up neat and spherical. It shows up lopsided, wobbling, and it has to shake off that distortion before it can settle down. And all the while it's settling, it keeps radiating. No longer a chirp now, but a fading hum. GW 190521 hummed at two frequencies at once, 63 Hz and 98, and both had died away inside about 30 milliseconds. Colin Capano of the Albert Einstein Institute put it the way I'd put it to a friend over coffee. A black hole rings like a bell, and the blend of fading tones tells you what the bell is made of. Read the ring down carefully and you come away knowing the mass and the spin of the new hole and of the two that made it. Now hold that up against what arrived in May 2019. No in-spiral, not a faint one, not a noisy one, none at all. The recording opens at the collision and closes with the hum. That missing movement is the whole mystery, and it's what nudged Chilai's team toward the suggestion that the in-spiral never reached us because it never happened here. What a wormhole would have to be. Fiction has thoroughly ruined wormholes, so let me say this plainly. They started out as mathematics, not imagination. While Einstein was still putting general relativity together, structures that looked like bridges kept dropping out of the field equations all by themselves. Nobody put them there. Decades later, when physicists in the 1980s started asking in earnest how you might actually cross the cosmos, those bridges picked up the name we use today. Strip away the film sets and a wormhole is simply a shortcut. A tunnel joining two far-flung regions of space-time, or maybe two entirely different universes. We have never seen one, and if we ever did, it wouldn't be the dark throat you're picturing. It would look like a sphere hanging there in space, and through that sphere you'd see the far side, warped, smeared, coming at you from the wrong angle, with the starlight around it bent into rings along the edge, just the way it is around a black hole. Past this point, everything is provisional, and some of it is argued over by people far cleverer than me. Take it as a map of what the mathematics allows, not a description of what's out there. The original version is the Einstein-Rosen bridge, a black hole at one end, a white hole at the other, opening out into somewhere else entirely. A black hole is a one-way door inward. Cross the horizon and there's no road back. A white hole is that same sentence read backwards. Nothing can ever fall in and things can only come out. And this isn't invention for the fun of it. Einstein's equations don't care which way time runs, so the solution describing matter collapsing into a singularity in the future can be run backwards to describe a singularity in the past throwing matter out. A white hole is a black hole playing in reverse. Join the two and you have a bridge. Unfortunately, the mathematics also tells us that bridge slams shut almost instantly, too fast for even light to slip across. Whatever carried our signal, it wasn't this. Scaffolding made of something impossible. In 1988, Michael Morris and Kip Thorne asked a simple question. What would it take to hold such a tunnel open? And Thorne is no fringe figure. He advised on Interstellar, and he later shared a Nobel Prize for the work that made LIGO possible in the first place. So when a man like that says something outrageous, it's worth hearing him out. Their answer was scaffolding. Prop up the narrowest part of the tunnel, the throat, against its own gravity, and it stays open. The trouble is what that scaffolding would have to be made of. It would have to be exotic matter. And let me say straight away, this is not antimatter. Antimatter is real, we make it in laboratories, and it has ordinary positive mass. Exotic matter is the hypothetical stuff with properties nobody has ever laid eyes on. Negative mass, negative energy density, negative pressure. Negative mass is worth sitting with for a moment. Push a normal glass to the left and it tips to the left. Push a glass with negative mass to the left and off it goes to the right. It accelerates against the very force you applied. Ordinary matter falls toward other matter. Drop a shoe and the floor collects it. Negative energy matter does the opposite. It is pushed away from things and it pushes back. And that outward shove is exactly what a wormhole throat would need to keep itself from caving in. None of this is forbidden, mind you. It breaks no conservation law, it contradicts none of the equations, and that is precisely why physicists can't simply toss it in the bin. It's permitted and unobserved, which is an awkward place for any idea to live. Which brings us to the obvious objection. Even if you grant a tunnel that stays open, why would a signal survive the journey intact instead of dissolving into noise? The answer, as it happens, may run far deeper than plumbing, because wormholes might be the hinge between the two theories that refuse to speak to each other. Entanglement. Wearing a different hat. General relativity handles the very large, gravity, spacetime, black holes. Quantum mechanics handles the very small, particles, fields, probabilities. Each one is spectacularly successful. Put them in the same room, at the centre of a black hole say, and the equations start producing nonsense. In 2013, Leonard Susskind and Juan Maldacena proposed a bridge between them, and the bridge is a bridge. Their suggestion was that a wormhole and a pair of entangled particles aren't two separate phenomena at all, they're one. Entangle two particles and they become a single system, no matter how far apart you carry them. Measure the spin of one and the other instantly takes the opposite value, whether it's sitting on your desk or off in another galaxy. Now that sounds like a violation of the universe's speed limit, and it isn't, for a rather subtle reason. Nothing is being sent. Each individual result is random, only the correlation between them is fixed. You can't use it to deliver a message, which is how relativity walks away from the encounter unscathed. What Susskind and Maldacena added is that this connection may be geometric, that entangled particles are joined by a wormhole so small it has no business being called a tunnel at all. The proposal goes by the name ER equals EPR, after two papers published in the very same year, 1935. The Einstein-Rosen bridge on the left of the equals sign, Einstein-Podolsky-Rosen entanglement on the right. Two of the strangest ideas in physics, born just months apart, and quite possibly describing the very same thing. The wall of fire that shouldn't be there. If that's right, it does something remarkable to the oldest quarrel in black hole physics. Quantum mechanics won't budge on one point. Information cannot be destroyed. And yet a black hole seems to swallow information for good and then quietly evaporate. Both of those can't be true at once. That's the information paradox, and it has outlasted several generations of clever people trying to put it to rest. In 2012, 4 physicists at UC Santa Barbara, the AMPS team, named for their initials, set out to settle the matter, and made it considerably worse. They showed that if you insist quantum mechanics holds, and that information gets out, then the event horizon simply cannot be the calm, unremarkable boundary relativity describes. It has to be a wall of ferocious radiation. an infalling astronaut wouldn't drift peacefully across. They'd be incinerated right at the threshold. Relativity says nothing special happens there. Quantum mechanics says you burn. That's the firewall paradox. ER equals EPR offers a way out, and it leans on a result Stephen Hawking found back in 1974. Quantum effects at the horizon make black holes leak, radiating themselves away over stretches of time that make the age of the universe look like a lazy afternoon. The open question was always whether that leakage carries any memory of what fell in, or whether it's just featureless noise. But if every escaping particle is entangled with a partner still inside, and if entanglement really is a wormhole, then inside and outside were never truly separated. The information was never sealed away. In principle, you could recover it from the radiation, and the wall of fire never needs to exist at all. The soft spot in all this was that ER equals EPR had only been shown to work in an absurdly tidy scenario. Two black holes sitting in perfect thermal balance. Real black holes are filthy things. They're feeding, spinning, being knocked about by infalling matter and quantum noise. And a theory that only holds for objects that don't exist isn't much of a theory. So in 2025, a team went hunting for the breaking point. They built a model of two deeply entangled black holes joined by an Einstein-Rosen bridge. Started from the pristine case, a smooth symmetrical tunnel, and then deliberately scrambled the entanglement, turning the chaos up notch by notch to see when the geometry would give way. It didn't give way. The tunnel stretched, roughened, bulged out into irregular segments. The shape they ended up with was christened the Einstein-Rosen caterpillar. But it stayed coherent, stable, crossable, obeying the ordinary rules of gravity all the way through. And in their standard models, no firewall showed up at the horizon at all. They built one on a chip. For our wave to have genuinely come through a wormhole, two things have to hold. Wormholes linking entangled black holes must be real and durable enough to carry a signal. The caterpillar tells us that's at least mathematically respectable. And information has to be able to make the crossing. In 2022, a group did that second part in a laboratory. They built a holographic wormhole inside a quantum computer and pushed information straight through it. That sentence deserves unpacking because it's doing an awful lot of work. It starts with Daniel Jafferis at Harvard. Back in 2016, he worked out something rather lovely. Take two entangled quantum systems, couple them together in one very particular way, and an operation on one side ought to hold a wormhole open if ER equals EPR is right, and push information straight through it. Elegant theory, with one rather obvious snag hanging over it. Could anybody actually build such a thing? 6 years later, Maria Spyropoulou and her group at Caltech did. They used Google's Sycamore processor to stand in for those two entangled systems, the pair that ER equals EPR says should be joined by a tunnel. In went a single qubit riding on one particle. Almost at once, that information smeared itself out across every particle on that side of the system, the way a drop of ink loses itself in a glass of water. At that point, by any ordinary standard, it's gone. Then the team applied a precise rotation across all the qubits, and in the language of gravity, that means firing a burst of negative energy down the throat, propping the tunnel open with exotic matter. And the information came back, not smeared, not in pieces. It reassembled on the far side onto a single particle, and precisely the entangled twin of the one it went in on. Ink out of the water, back into the drop. Spiropoulou said the moment felt like seeing the first data from the Higgs discovery. The field pushed back quickly, and fairly, I'd say. Several analyses argued the model was far too simple to stand in for a real black hole, and that calling it a holographic wormhole rather oversells what was actually built. I think that caution is right, and I also think the result still matters. What the experiment showed is that a system running on nothing but quantum rules can behave in a way that is mathematically indistinguishable from a wormhole in a gravitational theory. The two descriptions rhyme, even though the physical objects have nothing whatsoever in common. So, was it? Let's go back to May 2019, now with everything we've got laid out on the table. Here's what Chi Lai's team proposed. In another universe, two black holes spiraled together in the perfectly ordinary way. But instead of leaving behind one larger black hole, the merger produced a wormhole, one mouth over there, the other one here. We never heard the inspiral because the inspiral stayed on their side of things. Only the ring down leaked through, arriving in our detectors as a fragment with its beginning lopped off. Taken one at a time, the pieces are respectable enough. Negative energy can, in principle, hold a throat like that open. Information can, in principle, cross it. Put that way, the idea stops sounding ridiculous and starts sounding merely unlikely. The authors have an explanation for the brevity too. 1/10 of a second, one single pulse instead of the fading train of echoes a ring down ought to produce. Either the wormhole collapsed into a black hole almost immediately, or the later echoes were simply too faint for us to hear. None of this can be ruled out, but I want to be straight with you about the verdict, because the authors are straight about it themselves. Even with that missing in-spiral, a perfectly ordinary black hole merger in this universe still fits the data better than a wormhole in another one. So why does this paper matter? Because it takes an exotic idea and turns it into something you can hold up against real detector output. And that's a rare, precious thing to manage. The Caltech experiment showed that wormhole-like behavior can be made mathematically concrete, written down, and checked. The Einstein-Rosen caterpillar went further. It showed such tunnels can grow out of the mathematics of quantum chaos all on their own, rather than being placed there by hand. Put them alongside ER equals EPR, and they all pull on the same knot, tightening it. The notion that quantum mechanics and general relativity are two descriptions of a single structure, and that we simply haven't found the right words for it yet. And the instruments keep getting better. Since 2023, LIGO and Virgo have been running about 30% more sensitive, picking up a merger every 2 or 3 days. Think about that. 10 years ago, we could not detect gravitational waves at all. As sciences go, this one is still a toddler, wobbling about on new legs. Give it better models and sharper detectors, and perhaps one day we won't just confirm that wormholes exist, we'll send something through one. I'd hate for them to stay locked away in equations and screenplays forever. For now, we watch and we wait.